the important things we need to learn to do in chemistry is to determine whether we're going to form a solid or a precipitate in a water environment at the end of a chemical reaction. That is to say, one of the products becomes a solid, falls to the bottom in a water environment. This is going to be used for a number of things, but most importantly perhaps is to determine whether we have a driving force in a double replacement reaction. And in this lesson we'll begin to learn how to figure that out. So this is your homework that was due today. And what you're supposed to do with this is to predict whether the reaction will happen, and if so, write the correct products and balance the equation. To determine whether this reaction will happen, we're going to need our test references and need the activity series. We have a metal here that's by itself, and if this reaction is going to move forward, it has to displace something that's like in this compound. And so what it's like in terms of the activity series, excuse me, is this hydrogen ion here, the hydrogen in an acid. And you notice on the activity series, excuse me, there is a hydrogen ion here from an acid, okay? So the zinc, if it's going to react, has to be more active than a hydrogen in the acid. And zinc is higher, it's above the hydrogen. So zinc will displace the hydrogen, and therefore zinc's going to join up with the chlorine when it displaces the hydrogen. And the hydrogen then gets kicked out by itself. But hydrogen doesn't exist in its elemental form, excuse me, as just an H. It's an H2. Okay, it's a hydrogen gas. So H2 in the physical state is gas, because H2 is a gas. We talked about that yesterday. Now we have to balance this formula. So zinc has a 2+ charge. It says so here. It also says so on the periodic table with oxidation numbers. And it is also in a place on the periodic table where you can figure out its charge without any other references. Okay, so because of where it is on the periodic table, you can figure out it has a 2+ charge. So chlorine has a 1- charge. You can figure that out right here. You can figure it out from the periodic table that has oxidation numbers on it, and you can figure that out just by where it is on the periodic table. It's in column 17, or Roman numeral 7a, and all of those elements in that column in a binary compound meaning 2 elements, would have a 1- charge. And so since this is a 2+ charge and this is a 1- charge, I need to have 2 of these to have the same number of positive and negative charges, so they cancel out. So a 2 positive charge here is canceled out by 2 negative charges here, giving us a neutral compound if we have 2 chlorines. And so when we put it together into a formula, we use a subscript to show there are 2 chlorines bonded to that zinc. All right. So now we need a plus sign right here. And you would not know yet, but you will know today, that this is going to be aqueous. Okay, so I'm not going to count against you anything if you don't have that showing as aqueous. Okay? But now we have everything we need to balance the equation. We have all balanced formulas now. We're ready to balance the equation. To balance the equation in this class, you are required to use an atom inventory. So we're going to count up all of the atoms on both sides, and we're going to do it like this. We're going to write zinc and hydrogen and chlorine vertically. We're going to make a kind of grid or chart, if you will. And then we're going to count on from this vertical line here to this side. We're going to count everything on this side of the equation. So right now I have 1 zinc and 1 hydrogen and 1 chlorine. On the other side of this line, this vertical line, I'm going to count everything on this side of the equation. And I have 1 zinc, I have 2 hydrogens, and 2 chlorines. Okay? And so what we want to do is to use coefficients to get everything to be the same, to have the equal number of atoms on both sides. And you can't use anything else but coefficients. Once the formulas are balanced, you have to leave them alone. Can't change the formulas, but you can change the number of those formula units. So to get the number of hydrogens to be the same, we're starting with hydrogens here. I want to put a 2 in front of the species that contains hydrogen on the left, and that's going to change the number of hydrogens and the number of chlorines because there's hydrogen and chlorine in that species. This 2 multiplies the number of atoms for this whole chemical formula. And so we're going to have 2 hydrogens now and 2 chlorines, and everything's equal. It's that easy. All right, so now we want to count up everything that we did and give you points for it. Well, except for assigning this aqueous here because you wouldn't know that yet. All right, so we've got a 2 here. That's 1. This zinc and chlorine and the subscript 2, that's all worth a point for 4. There's a plus sign, hydrogen, and H2 and gas. Okay, so that's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3 for 10, 11, 12, and cancellation is 13, 14, 15, 16, 17, 18, 19, 20, and then you get 1 point for having the grid. Okay, so that's 21 points for this problem. All right? Okay, I recounted and it's actually 22, not 21. Okay? I missed something when I was counting it, trying to stop and explain things. So for this next problem then, we've got iron by itself, and it's here in the second position instead of the first. It doesn't matter. Doesn't matter whether it's first or second. But iron is a metal, and if it's going to react, it has to displace something it's like in this formula. And the thing that it's like is this metal ion. So in terms of using the word like here, we're using either metals or halogens. Although metals can also include hydrogens in an acid or even water sometimes. Okay, even steam or water can be something it can displace. And if you notice, that's the way it's arranged in that activity series. So iron can displace another metal, possibly, if it's more active, and we'll know it's more active by its position on the activity series. So I'll slide this up a little bit. We'll look at the activity series. And iron is located right here, and nickel is located here. So iron is higher on the activity series. It is more active than nickel is, so it can displace the nickel in an ionic compound. Okay? And so I'm going to write iron with the perbromate ion. And I want to have nickel then, since it got kicked out, it's by itself. We know that metals, except for mercury, there is one of the metal that tends to be a liquid, but you don't know about that. It's kind of rare. But almost all the other metals at room temperature and pressure will be a solid. So we'll list it as a solid. We need to figure out how to balance this.
That's only thing that confuses me. Like, how do you know the nickel from the solid or different gas?
Well, metals are solids.
Oh, yeah.
Okay? So here's iron. And it says that when we're doing these single replacement reactions like this, and we form compounds with an iron, it becomes iron 2. And so we know this iron here is going to be iron 2. To know the charge on the perbromate ion, you've got to go to the common ions list. Now, if you're in an honors class or an AP chemistry class, you're going to have to memorize some of these. Okay, you won't have these on a chart to be able to use. But perbromate has a 1 negative charge. Okay, so perbromate has a 1 negative charge. And so for every iron, I'm going to need 2 perbromates. Okay, so the formula for this compound has to be Fe parentheses BRO sub 4 parentheses sub 2. The 2 outside the parentheses tells us we have 2 perbromates. And without that parentheses, it would mean we had 42 oxygens, and we don't need 42 oxygens. We need 2 perbromates. All right, and we still need a plus sign here. And now we're ready to write an atom inventory and balance the equation, or check the balance. So we've got nickels and bromines and oxygens and irons. And we need our grid. And we count up all the atoms we have. We've got 1 nickel on the left. We've got 2 times everything inside the parentheses, so we've got 2 bromines. And since I've got 2 times everything inside, and inside I have 4 oxygens, that's 2 times 4 or 8 oxygens. And I have 1 iron. On the right-hand side, I've got 1 nickel. I've got 2 bromines, I've got 8 oxygens, and I've got 1 iron.
So it's balanced.
And it's balanced. So, but you have to show me it's balanced, because like all good Missourians, we expect you to show me. Okay? All right. So let's count up everything you had to do. You had to put the iron over here. You had to put the parentheses and the bromate ion, or perbromate ion, I'm sorry. You had to have, you had to close the parentheses. Well, since you got the parentheses in the beginning, and let's just give it for just the parentheses, both sides would be 1 point. Subscript 2, plus sign, nickel, solid, 1. So that's, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and the grid is 20 points. Okay? All right, then. In the next problem, then, we've got chlorine over here. Now, chlorine in its elemental form is Cl subscript 2, and it's always a gas. And this is a halogen. It's not a metal. If it's going to displace something in its compound, it can't displace the metal. It has to displace the halogen, if there is one. And fluorine here is also a halogen. Okay? So looking at the activity series, we need to figure out, will chlorine displace fluorine in a compound? And so we look down here at the activity series of halogens, and we see that fluorine is above chlorine. Chlorine is not more active than fluorine. Okay? Chlorine is less active than fluorine, so chlorine will not displace fluorine. So really, the only thing you have to do here is write that. And so that's worth 2 points.
And that NR means
No reaction. NR means no reaction.
Only because can you say that again?
All right, then. Here we have another halogen. We've got fluorine, and here's bromine, another halogen. Looking at the activity series, then, we see that fluorine is higher and therefore more active than bromine, so fluorine will displace the bromine ion. And so fluorine is going to join up with manganese on the other side of the equation. We're not going to balance the formula yet. You can't just carry subscripts over. The little thing that I say, the little saying I use is subscripts only travel if they're part of a polyatomic ion. This is not a polyatomic ion, so this subscript doesn't travel over here automatically. Okay? And then we're going to have bromine over here by itself. All right, now once we've put them over there, now we're going to figure out what kind of subscripts to use. Manganese has to have some kind of charge, and we look for it here. Since this is a single replacement reaction, and since the activity series deals with single replacement reactions, we can find the charge number we want on this particular activity series. Now, there are some activity series that do not have the charges written out for students, and they have to kind of figure it out another way. But in this class, we use one where there are charges written with the activity series of metals. So manganese is going to have a 2+ charge. And fluorine we can see here, and on the periodic table with oxidation numbers, and by its position on any periodic table, we can see that in a binary compound, it has a 1 negative charge. We can also see then that we need 2 fluorines. We've got a 2+ charge on the manganese. To balance out that 2+ charge, we need 2 negative charges. And the only way to do that is to have 2 fluorines. And so when we write the formula and balance the formula, it's got to have a subscript 2 on that fluorine to show we have 2 fluorines. Or fluorides here, because it's an anion, a negatively charged monoatomic ions, and then we call those ides, like fluoride. And then bromine here is always going to be diatomic, and it's always going to be a liquid. Now then, let's balance the equation. We've got fluorines and manganese and bromine. And we're going to make this kind of grid here for the atom inventory. We have 2 fluorines on the left, 1 manganese, and 2 bromines on the left. On the right-hand side, I've got 2 fluorines. I've got 1 manganese and 2 bromines, and so the equation is balanced. Okay? All right. So we had to put manganese and fluorine together. Now remember, even though I've got a 2 here, you don't just take this 2 and move it over. You have to figure out whether that 2 belongs there or some other number belongs there. Okay? If you just carry it over, you're going to get a wrong answer. Remember, the only subscripts that travel on their own are those that are part of a polyatomic ion, like this 4 on the perbromate up here. That one traveled automatically because we keep the polyatomic ion together. Polyatomic ions tend to stay together. Tend to. They don't always, but they tend to. All right, now, let's count up what we're going to give for points. 1, 2, 3, 4, 5, 6, 7. You don't know yet that this is an aqueous compound. We're going to get to that shortly. All right, so I got 7 so far. 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17 is for the grid for our atom inventory. So that's 17 points. Oop. And if I've added everything up right, that should come out to be 61 points total for everything. So we're going to use this single replacement reaction to look at whether or not something is going to be aqueous or not.
It has the date and everything. And I have a legit mom on it.
All right. So when you get this far, you have predicted the products, you balanced the formula, you found that copper's over here by itself because copper's more active than the nickel is. I'm sorry, nickel is more active than the copper is. Now we're at the point where we can use the solubility rules to figure out the physical state. So listen carefully. Solubility rules only are used if water is around. Solubility rules are only used if water is around. Solubility rules are only used if water is around. And it says right here, these solubility rules are for ionic compounds. So it only applies to salts, ionic compounds. Actually, there's a class of ionic compounds that aren't really salts, so ionic compounds is a better term here. And there are 2 categories. There's a soluble section at the top and an insoluble section at the bottom. Now, soluble means dissolvable, and we're talking about dissolvable in water. So when we say soluble, it doesn't mean that it is dissolved. It means that if there is water, then it is dissolved. Okay? So you have to have water. That's a precondition to find one of these things to be aqueous. So if it's soluble, it will dissolve. If there's water around, it will be dissolved, and we'll call it aqueous. Okay? If it's insoluble and there's water around, then we'll say it's not dissolved, and we'll call it a solid. Because what's going to happen is these kinds of salts are going to fall to the bottom. And solids that fall to the bottom out of a liquid are called precipitates. And you're probably familiar with that term, precipitation. Okay? This falling out of at the bottom, that's precipitation. Well, you're also aware of precipitation come in the terms of rainfall or dew on a cold morning or whatever. Okay? Any kind of more organized physical state that drops out of a less organized physical state is precipitation. So liquid coming out of a gas, like rainfall out of the air, that's precipitation. Any kind of solid that falls out of the bottom of a liquid is precipitation. Even the silt that comes out of a river at the end of the river where it goes into the ocean, that's a type of precipitation. Even though it technically is not actually dissolved, it's still called precipitation. All right. So having laid all that out, I want to also make sure you're clear with soluble and insoluble are relative terms. The fact is that everything dissolves in water. Literally everything can dissolve in water. But some things dissolve very little. And so when we say insoluble, we're meaning it dissolves very little. And down here at the bottom, it actually gives you a definition of that. It says insoluble means a precipitate forms when equal volumes of a 0.1 molar solution or greater are mixed. Now, you don't know what that is yet because we haven't gotten to our unit on solutions. When we get to our unit on solutions, this may make more sense to you. Okay? But for now, it's good enough to know, you're doing well enough to understand that insoluble means very little dissolves, and we assume for the purposes of this exercise that none dissolves, and soluble means a lot of it dissolves. Okay? That make sense? Doesn't mean it's infinitely dissolvable, because if I put enough table salt, which is soluble in water, I'll get to a point where it won't dissolve anymore, and I'll get solids in the bottom. But it's still soluble because a lot of table salt will dissolve in water. Now, back to how to use this. What I want to do is to find in the solubility rules some reference to this chemical. So I want you to take a minute, and if you want to, you can work with a partner, a learning partner near you, where you're sitting, and look and find some reference to this chemical in the solubility rules. Okay. Quillia and Reagan think it's soluble.
I do too.
You think it's soluble? Okay. Well, I'll tell you what. Why don't we do it instead of me saying so? Why don't we have Reagan tell us? Oh, well, she's busy with something. Okay. Quillia, why don't you tell us? What is your name? Quillia? What? What's your name? Quillia. Okay. Okay, well, this is not a chlorate. You got the right answer, but for the wrong reason. Anybody got something different? Chloride. It's right here. It's right below it. Okay, this is a chloride. When we named these, we said it was a chloride. We named this nickel chloride. Pay attention up here, please. It's very important that you pay attention up here. Okay. Chlorides. This is a chloride. When we learned to name compounds in the last unit, we found that this was called nickel chloride. Okay? It's an ionic compound. Use the ionic naming rules. Okay, the nomenclature system for ionic compounds. It's a chloride. It says that all chlorides, they're in the soluble section, except if they're bonded with silver, lead, and mercury. So you have to be careful. Just because it has chloride here doesn't mean that every chloride compound is going to be soluble, because chlorides that are bonded to silver, lead, or mercury 1 are not going to be soluble. Okay? All right, but this one is because it's not silver, lead, or mercury. So this is going to be soluble. If it's soluble, and if there's water around, it will be aqueous. There is water around because there's water to dissolve this chemical. So this whole reaction is taking place in an aqueous environment. Just because I have one chemical that says aqueous, it means there's water there. So we can say this. It's soluble. If there's also water around, then it will be aqueous. Soluble means it will dissolve, so it doesn't dissolve unless there's water. So if it's soluble and there's water, then it's going to be solubilized, which means aqueous.
How do we know if there's water?
Because it says so right here.
Oh.
Okay. Now we're ready to balance the equation. All right, so this is already balanced, but you have to show me the atom inventory because I'm from Missouri. Okay, let's do another one. I'm going to let you work on this yourself.
Why are you here? Let me tell you. He ain't in there. I'm on 16. Just forget it. I forgot how it is.
All right, you have everything you need now to solve this problem completely. Please do so. All right. So, sodium and calcium are both metals. If a reaction is going to occur, the part that's by itself has to be more active, and calcium is more active. It's higher on the activity series than the sodium is. They're right next to each other, but calcium is a little bit higher. So calcium can displace and does displace the sodium, and so we get calcium with fluorine, and we get sodium by itself. We know that sodium is a metal, and metals except for mercury, at least in your knowledge base, are all going to be solid, so we can call that a solid. We don't yet know the balance for this, but calcium has a 2+ charge. It says so right here. And fluorine has a 1- charge. It says so right here. You can also look up those charges on the periodic table with oxidation numbers, and you can tell what their charges are by their position on any periodic table. Fluorine has a 1- charge, so I need 2 fluorines. And to balance the formula, then I need 2 fluorines written like this. Now we're going to look at the solubility rules to determine whether or not this is going to be soluble or not, an aqueous. So there is water around. We know that because there's an AQ next to this compound. That means that this whole thing is taking place in an aqueous environment. So for fluorides, they're listed right here, and it says all fluorides are in the soluble section. So they're soluble. If there's water, they will dissolve unless they're bonded with group 2, lead 2, and iron 3. Well, guess where group 2 is?
Fluorine.
Calcium is in group 2. Calcium is in column 2 of the periodic table. It's an alkaline earth metal. It's in group 2. So this is not soluble. This is going to be solid. Okay?
So all fluorine is 2.
All right, so we're ready to balance the equation now. We've got sodium and fluorine and calcium. We've got 1 sodium, 1 fluorine, 1 calcium. Over here we've got 1 calcium, 1 sodium, and 2 fluorines. To get 2 fluorines on the left, I need to put a 2 coefficient in front of the species containing the fluorine, which changes the number of sodiums and fluorines and gives us 2 sodiums and 2 fluorines. And to get 2 sodiums on the right, then I put a 2 there, and that changes this to a 2, and everything's balanced. All right, so that's how to figure out whether something's going to be soluble for single replacement reactions. And let me tell you something about single replacement reactions. We figured out that single replacement reactions will occur if the substance that's by itself, the element that's by itself, is more active than the substance that's like it in a compound. Okay, that's the way we determined a driving force. So a driving force is what makes a reaction take place. If there's not a driving force, it's no reaction. If you have a driving force, there are products. We're now going to talk about double replacement reactions. And in double replacement reactions, there's a different kind of driving force. Okay? And in double replacement reactions, well, first of all, let me tell you this. Single replacement reactions, you figure out the driving force from just the reactants. You didn't have to write the products to figure out if there's a driving force. That's not the case with double replacement reactions. A driving force is what makes the reaction move forward. This driving force is there because calcium is more active than sodium. Okay? All right. So a driving force in a double replacement reaction is one of 3 things, and it's all about what is made, what products potentially are made. Okay? So for double replacement reactions, the driving forces, that which makes the reaction actually occur, are all about what is formed, what is on the right side of the equation, not what's on the left side of the equation. It's all about the products and not the reactants. Single replacement reactions is all about the reactants. Double replacement reactions is all about the products. So the first driving force I want to tell you about is the formation of. That is to say, we're going to make on the right-hand side of the equation a product formation of a solid, or you could say it's also called a precipitate. Okay? That's a driving force. Now, these driving forces apply to those reactions that are taking place in an aqueous environment where water is present. Okay? Number 2, if you have a double replacement reaction in an aqueous environment and one of the products made is water, it doesn't mean that water is just around, but there's a product, a chemical formula on the right-hand side of water, then that means we're forming water in the reaction, and that's a driving force. The third driving force is the formation of a gas. In a double replacement reaction, the front part of one chemical switches places with the front part of another chemical. So if we have, say, something like this, let's see, we were using calcium a minute ago. Yep. CaCl2, which is aqueous, and we have, let's see, how about iron 3? Nope, that's good. How about something simple, K, F. Okay, all right. If we have two reactants like this, these are two ionic compounds. If a reaction is going to take place, I have a 2-part compound and a 2-part compound. If a reaction is going to take place, the front parts are going to switch places. Okay? This is a double replacement reaction. If a reaction is going to take place, the front part of this has to go with the back part of that, and the front part of this has to go with the back part of this. And we would get these products, at least when we initially put them together. Alright? So all I do is switch the front part and the back part, but I don't use subscripts yet over here because subscripts only travel if they're part of a polyatomic ion. Before I do anything else, I want to go to the solubility rules and see if I have evidence of some kind of driving force. I'm not forming water. Neither one of these are gases, so the only possible driving force is the formation of a solid. Okay? So let's see. Chlorides, it says, are always soluble unless they're bonded with silver, lead, or mercury, and that's not any one of those. So this is aqueous. So there's no driving force from this chemical. Fluorides, it says, are always soluble except when they're bonded with a group 1 metal. Calcium's a group 1 metal, so this is forming a solid. I'm sorry, group 2. I did say group 1, but it's group 2 it says here. Okay? Fluorides are soluble except with a group 2 metal, lead 2, or iron 3. So this is going to form a solid. Okay? So we have a driving force. This reaction moves forward. We have something we need. That's the formation of a solid here to make this reaction go forward. Okay? Now we can balance the formula. Then we can balance the equation. Okay, now I haven't written out an atom inventory because, I'm just trying to show you this in the short time we have left. Okay? Do you understand what you're doing? You're figuring out from the products that can form whether there's a driving force. And the formation of a solid tells you there's a formation of a driving force.
Why put random Oh, did you work it out?
Yeah, I kind of worked it out in my head.
Okay.
Okay? So don't confuse this with F2 being by itself and forming a diatomic gas. This fluorine here switched out and joined up with This is in a double replacement reaction. It doesn't form F to the gas. It forms a bond with the calcium. Okay, all right. Now this is one homework problem. You don't have to balance the equations. You don't have to do anything but predict the products and determine if a driving force is present. Okay? That's all that's required.
Wow. What we doing? So all I gotta do is
We got 4 days to do this, guys. That's ahead. I got 3 days.
Now then,
What's this? Unit 5?
yes. In addition, I'd like to do a lab on Monday.
No.
In addition, I'd like to do a lab on Monday. Okay? In addition, I would like to do a lab on Monday.
Is it gonna be in the notes?
No, listen please. In your Google folder is a pre-lab document for a single replacement lab. Okay? It's a single replacement pre-lab. Okay?
What do you
So
mean by
listen. All you have to do,
Take 50 seconds.
have a seat please. All you have to do is look at the two reactants and figure out if, because I have this reacting with this is a single replacement reaction, will there be a reaction? That's what goes under prediction. If you think there's a reaction, you have to tell me why you think there's going to be a reaction. If you think there's not going to be a reaction, so you know when we figured out in a single replacement reaction there was no reaction, tell me why. That's what goes under explanation. Okay, it doesn't seem very hard, does it? Now, now look, hold on. I'll get to your question in a moment. In addition to that, guys, hold on a second before you walk out. You need a chart, and it says so in this document, for your for your lab results. So you're going to have a chart that looks very similar to the one that you're doing as pre-lab in your lab notebook. Huh? No. You must write it in your lab notebook. Leave enough room. You can put this, I've got it on one page, but you can put it on 4 if you need it. Make sure you leave enough room for what you need for this lab when you take the notes in the lab.